Hello, everyone. Thanks for joining us today. Today we have, this is our 7th session for the series. Thank you all of you to follow us along, to attend. For some of them, if you miss some of the previous sessions, all of the sessions recorded, you actually can review the previous sessions on the YouTube. I will post the link to the YouTube channels. Feel free to say hi in the chat. Just introduce yourself. It's always exciting to see attendees join from all over the world. You can say, your background, which cities, countries you join from. That'd be great. For today's session, it's a workshop for about 2 hours. So actually this is we hosted these sessions a couple of times before. I think today's session is going to be a little bit update for more on the interactions. So, so before we get started, just a quick introductions on the IBM, the communities team you want to.
Yeah, can you guys hear me? Can you hear me okay? Yeah, hey, hello everyone. Thank you for joining today. My name is Tim Bonneman. I'm with the IBM Data Science community. We are a venue with now well over 13,000 people, data scientists, machine learning and AI experts, and learners. We provide lots of resources and lots of opportunity for you to meet peers and tackle these exciting topics together. If you join the community now, we have a special offer. You get a 1-month complimentary access to select IBM courses. It's an awesome package of resources and learning. Highly rated, and definitely check it out. The link is on the slide. I'll also put it into the chat. And yeah, check us out. And I hope you enjoyed today's session. And with that, I yield back. Thank you.
Great, thanks team. I think, again, these communities really create a lot of resources to learn the AI machine learning. And so data science is a great place to check it out. I do recommend it to take a look at the website to use these offers. Before we get started, just a quick logistic remind. Again, for the Q&A, please using Q&A tab for the questions to Austin, to the instructor. In the chat, you can for other communications or talks. The questions in the Q&A is much easier to manage and to track. If you prefer to raise your hand to speak to us, you can raise your hand to speak. We can allow to unmute you. But that's probably going to be at the very end. So in the middle, please just type using the Q&A tab to ask your questions. The session is recorded. It's going to be available on YouTube shortly after the session is done. We actually created a playlist in the AI Camp YouTube channel. It have all of the previous sessions, so it's a one-stop shop place to see watch all of the previous sessions. You can just go to YouTube to search AI Camp. You should be able to find the channel and then go to the playlist. I can also post the link to the chat too. For the networkings, for other chat and offline discussions, you can feel free to join this Slack channel. We have a very large community Slack discussion group. There are a couple of channels. One is the jobs, another one is events. So feel free to join for all sorts of discussions on the AI, machine learning, and data science. So again, for today, we're going to have the 2 hours workshop. I think that's pretty much I have. Austin, it's all yours.
Awesome. Thanks so much for the intro, guys. I really appreciate it. And thanks everyone for being here and being willing participants. And with that being said, let's dive into the content. Before we start, I would just like to let everyone know this will be hands-on, so there'll be a coding session. Here, let me share my screen. So with that being said, I would just make sure that you have some kind of, IDE, Jupyter Lab. That's what I'll be doing it in. And then on top of that, I would make sure, sorry, it's hard to see my UCI. You want to make sure that you download this data set. So you're just going to go and download the data folder, and we will be using the full data set for our interactive session. And once again, it'll be done in Jupyter Lab. If you're missing any of the dependencies, I'll show you how to do that. We'll just do a simple pip install. But yeah, I will copy this link into the chat real quick. So this is the data you will need. Awesome. All right. Yeah, and then if you have any questions, feel free to drop them in the Q&A tab. And if it's something really pertinent or something that's going to, increase everyone's knowledge, then Tim will politely interrupt me and bring that question up, just because I have the inability to look at the Q&A and do the talk at the same time. So with that being said, let us begin. All right, cool. So yeah, so today we are going to be talking about explainability. We're going to, roughly define what that means and then see what it looks like in practice rather than just, a theory. So this is a workshop. There will be code. And if anyone needs anything beyond the scope of this, I'm available at the IBM community, like Tim said, via email, LinkedIn, and then I'll also post all of the code on GitHub. So you'll be able to, clone it and get some more hands-on experience, improve it, do whatever you feel like you need to do. So let us begin. So I always start with this slide as the first slide, just because I think it kind of sets a good precedent of what we're going to be talking about. So the first one is something popularized by Mark Twain. It's one of my favorite quotes. It's the idea that there are three kinds of lies. There's lies, damn lies, and statistics. The idea being that how you frame and how you relay information can affect how the information is received. It sounds simple in theory, but when it happens, in the wild, in our day-to-day lives, it's not something that we are quick to observe as humans, just the way our brains are wired. So the idea is, telling somebody that something is 90% accurate is equivalent of saying, this has a 10% error rate. Those are, the same fact, just, one's framed as counterfactual. The idea being how you frame these is going to leave, who you're explaining to in a different, in a different state. So that's kind of the idea behind that quote. The next one is George Box. I'm sure everyone's heard this. All models are wrong, but some are useful. Idea meaning, we can get 100% accuracy on an MNIST model, but what does that actually mean? What is the trade-off? Things, things beyond the scope of the actual model. So that's that. And then the last one is, what I experience in my day-to-day as a data scientist, and I'm sure other people can kind of relate to this, is why did you do that? And the idea is anyone and everybody will ask you this question, from your manager to other data scientists to plausibly an end user or even a regulator. Why did you take the series of actions you did to arrive at some desired outcome? Or what actions did you take to lead yourself to an undesired outcome? How do we mitigate that? And, how do we alleviate some of the shortcomings, that are captured by that question? So in an easier way of explaining it, why are you here? You are here to, by the end of this, understand what is the impact of this visualization? Where is it useful? Where is it not useful? How can it help you, once again, mitigate against some, common failures of the data science workflow? As well as, how can it augment your current workflow to, perhaps make things a little bit more digestible for, other data scientists, yourself. I'm sure everyone has had that feeling where you code something, come back 2 weeks later and ask, like, who coded this? So, this is the idea of how are we going to explain things in like terms to, different personas. Oh, what just happened? I'm sorry, my computer just like locked out. All right, cool. Can everyone still see? Apologies. Sorry about that. Technical difficulties. So back to this slide. Yeah. So explainable workflows, they're not built to, replace your work or greatly alter it to an extent where it's going to be twice or 3 times the work. What we're trying to do is augment your current tooling and workflows in a manner that will, once again, help alleviate and mitigate against downstream errors and, procedural tasks. So that way you have more time to understand why you are doing things rather than simply focusing on the how things are done. So once again, high level, looking at these bullet points. So the idea behind this is to empower you with your the ability to rapidly prototype and define a solution space for a desired outcome. What that really means is, once again, gives you more time to understand why things are occurring rather than how they are occurring. You can provide timely and relevant explanations to different stakeholders based off their persona, whether that's a regulator or an end user and everyone in between. It will augment your ability to deduce where things can go awry, debug it, and resolve it with your data science team, take it to data engineering. It's about problem isolation and problem alleviation. And the way we do that is through this workflow. And then the last part, and I think the most important part, is to reduce your overall time to reach a solution while increasing and maintaining trust and transparency in what you do. Because as a data scientist, the burden of proof kind of falls with you, as you are at the ground level of these models and different, things being built out. So when problems occur, people are most likely going to, go to your manager, who in turn will come to you. And if you're unable to adequately explain, why a system failed or why a system is mispredicting something or, beyond the scope of simple things like that, if you can't adequately track your own work and explain it to others, how can you make the assumption that others can do that without you there? So with that being said, we are going to now kind of just go into, some rudimentary definitions, so that way everyone is using the same language and has an understanding of what we are trying to do in a little bit more concerted fashion. So the words interpret and explain are often ambiguous at best and interchangeable at worst. So we're going to use the Merriam-Webster definition of each word, and at the same time, we're going to add a little bit of our own definition. So interpret, to explain or tell the meaning of, present in understandable terms, conceive in the light of individual belief. You guys can read the rest. But the way we are going to use it is interpret is a static task. You get your MNIST data, you make sure it's in the proper format, you build your model, and your model performs to some degree based off the metric you're using. So if you're using like cross entropy or just accuracy, etc., you interpret that metric at the end of the runtime. And why it's static is because all of the work's been done, and now you are viewing a metric, and it's up to you to ascribe the reason behind that phenomenon. The phenomenon being whatever metric you're viewing. The model and data are kind of they're not the focal point of this. It's the idea of you are doing something once in real time and trying to relay different facts to one another in order to interpret why this occurred. So another example would be if your last layer of a neural network is a softmax, which makes everything a summable probability to 1, and you get a negative probability, you could interpret that as there is some error or some we built something into the model incorrectly, or we fed data incorrectly. That's what the interpretation is you observe a phenomenon and you ascribe it to something. Oh, I think there's negative probabilities because of X, Y, or Z. And the reason I'm interpreting this to begin with is because based off of my knowledge of softmax, we should not have negative probabilities. So I hope that makes sense, because we will be using this when we do our hands-on approach. Explain, very similar. This is once again from Merriam-Webster, very similar definition, but the way we're going to use it is explain is the dynamic. It's the dynamic part of this workflow. You can think of it as an iterative or even a recursive process. The idea being you can interpret one statically, and say we ascribe our negative probability using that softmax example to improperly building our neural network or improperly shaping our data, and we want to deduce if that is true. The way we would do that is by iteratively going through it. So maybe we keep everything the same and change one thing at a time. So maybe we keep our neural network or whatever model we're using exactly the same, and all we do is change the format of the data. And then we run it again and we see, are our probabilities all positive? Are we still getting, the desired metrics that we're looking for? If that's not the case, then, we can kind of deduce that, maybe data formatting is not the problem here. Maybe it is in the model architecture, and then we change something about the model. So the idea is to, make incremental changes so that way you can adequately understand why these errors are occurring and, and fix it, and then communicate it to the relevant stakeholder, right? Because if you have no idea where the problem lies, but we all understand there's a problem, and your manager or a teammate says, hey, there's a bug in the code, how long is it going to take to fix? If you don't have an understanding of where that problem may be arising, or if you don't have the tooling to discover where it is, then how can you give an adequate time frame of when this will be resolved, or how it will be resolved, and ultimately why it should be resolved? So as you can start to see, 7 slides in, all these concepts are pretty interconnected, and the idea, by understanding each one of them as a individual component, you can understand the workflow at a kind of global level of how each one of these steps and ideas and theories fits with one another to make it conducive for you. Because once again, we're not trying to make your work redundant or give you additional and laborious tooling. We're simply trying to augment your work in a manner in which best serves you, your customer, your stakeholders, and allows you to retain, a sense of trust and transparency in the work that you're conducting. So what does this really mean? This is taken from Dennis J. Hinton's paper on causal explanations. I can link people to that if they'd like it. So what does this really mean? And this is his language. I didn't put quotes on it, but it is from Dennis J. Hinton. So the verb to explain is a 3-place predicate. Someone explains something to someone, which is exactly the phenomenon we were describing before. So that is the idea of explaining in real world terms, beyond just a dictionary definition. And then the next part is causal attribution. So we attribute a process to some phenomenon, and that is what the origin of what we're observing is. Once again, this is the idea of causal attribution, and at this point, many people have said this, but correlation does not equal causation. So just keep that in mind. I mean, it's okay for us to interpret and say, I think the root cause of this error is this, but just because, there's some corollary there doesn't mean that might be the cause. And that's the idea of why this is an iterative workflow, so that eventually you can try to isolate what is the cause rather than just what is some arbitrary corollary. So yeah, that's what these two terms mean. And once again, if people want the paper, let me know. So we more loosely define the idea of explainability as the ability for a data scientist or another IT professional to results to be understood and interpreted by other data scientists and stakeholders. Because once again, we use the word interpret here because if you're not there and you're giving a write-up or comments in your code or things of that nature, how can someone statically view what you've done and interpret it and come away with the same, with the same ground truth that you did as you did this explainability workflow? The idea being, if something's muddled or something's difficult to understand, they will call you in to explain it to them. And that's kind of your, fail safe. And if you're still unable to relay the factuals and counterfactuals that, govern what you're showing, then that kind of indicates to you that there's still work to be done. So this is, because we were talking about personas earlier, so this is just a visualization to kind of, this is not a one-to-one mapping of reality, but the idea being this is a pretty good placeholder for people to, think about this. And the idea is we have an experience as our x-axis, we have technical skills as our y-axis, and then we have need as our z-axis. I used negative and positive numbers just because I thought that relayed the information in a more easily understandable manner. By no means am I saying that someone can have like negative experience or negative technical skill. It's just a concept to make the point. So with that, data scientists are someone who's relatively experienced, 2 to 5 years, pretty darn technical, but their need for an explanation may not be of the greatest importance in comparison to other people, other personas on this map. So a data science manager may be someone who is very experienced, very technical, and also has a high need for explanations because they're the one who may have a better interface with stakeholders or end users or, other teams who need to understand the work that you're doing. On the flip side, we have regulators who may be someone who's not very experienced. Maybe they don't work at a tech company, but they work for the government. They're most likely, more often than not, very technical, and they have the highest need. The idea being they are the ones who are the final layer of scrutiny. So if you work in a highly regulated industry, such as finance, health, things of that nature, if you're building neural networks that can help and discriminate against fatty tissue and cancer, that's going to have a much higher degree of explainability because the threshold for incorrectly classifying someone is the stakes are much greater versus if you're building a iPhone app that can tell you if it's a cat or a dog. So that's why regulators kind of have the highest need. And regulators aren't necessarily in every industry or every vertical, but when they are, they once again have the highest need. And then ultimately, the end user. So if you're building some kind of application or some kind of model that's even if it's used behind the scenes, so like for loans, for college applications or job applications, things of that nature, the end user is going to have a high level of need in the sense of if you were rejected from a loan, why were you rejected? What reasons led to this outcome, and how can the end user learn to improve things so they can get that loan, or so they can get a job, or so they can go to that college? The end user may not be technical, and they may not have experience. Your end user might be a mechanic who's technical, but that's not in the same sense of someone who's building data science routines and doing data science workflows. At the same time, an end user could, be a relative of yours, or, that's how I like to think of it, because then that kind of really grounds this idea of doing things in a trustworthy and transparent manner into the scope of reality. Because you don't want to, put things out there in good faith that disproportionately affect people because of underlying mathematical nuances or poorly built models. So that's the idea behind this graphic. This is just a research overview. Once again, this is all listed in the bibliography for the slides, which you can find online. And if anyone wants these papers, these should all be on Arxiv to the best of my knowledge. If not, I can just send it to you via email. So the first one is by Cynthia Rudin, Stop Explaining Black Box Machine Learning Models. The motivation behind that one is a thing called Compass. It was a 2016 it was protected by intellectual property rights. It was a bespoke and customized algorithm that the Florida penitentiary system used to gauge people's recidivism rates. And what they found is that the algorithm disproportionately categorized, Black people as more likely to be, revisit jail than white people, and it was disproportionately affecting them, and it wasn't based on, factual data, to the extent of it was built behind IP, so no one could actually debug the model and deduce why these results were occurring. So what Cynthia Rudin and her team did is they took a bunch of subject matter experts and built out a rule-based system that not only worked in a more equitable and equal fashion, it also, properly ascribed, the phenomenon they're trying to predict, whether or not someone's going to go back to jail. It was more accurate in that regard. And the idea being is she's writing this paper, and the idea, like, we shouldn't necessarily be trying to explain black box models. We should be trying to build robust, transparent, and trustworthy models from the very beginning. So that way we don't have things like the Compass initiative where people are being disproportionately affected, because that's, detrimental to society, and, at a localized level, detrimental to the people who are being disproportionately affected's livelihoods. So that's kind of, a motivational idea behind why this stuff should be good beyond, or should be used beyond the technical aspects. These are systems that are slowly becoming more and more widely used, and in that vein, it's up to us as data scientists, machine learning engineers, data engineers, everyone in the technical stack who sits on deployed models to move these technological innovations forward in good faith. The next one is the XAI program, the Explainable Artificial Intelligence program. That's from DARPA. That's just kind of showcasing, they took like a few $1 billion and they basically allocated it to different universities to build, explainability interfaces, explainable models, things of that nature. So that way, once again, we can kind of move forward in a trustworthy and transparent manner. Why should I trust you? That's the paper on Lime, which is an algorithm we'll be using. Type-driven automated learning with Lale. That's another paper on a toolkit we will be using towards robust interpretability with self-explaining neural networks. That's kind of like way off on the technical deep end. That's an MIT paper where it's it's beyond the scope of this talk. It's very technical. I'm not sure if it's been applied in practice yet, but it does have some interesting theoretical ideas and some interesting applications beyond the scope of this talk. And then the last one is an IBM paper, TED, Teaching AI to Explain Its Decisions. That's a good one. That's kind of a theory as well as an applied paper. So before we go into the demo, the last things I'm going to leave you with is where the demos live. So this first GitHub right here, that's where you're going to find the AI Explainability 360 toolkit from IBM. The second one is Lale's GitHub, which is for semi-automated data science. So we're going to use that for rapid and robust prototyping. And the last one is a masterclass that myself and my team put together. And that's around 90 minutes of content with a quiz at the end. And you can find that at the link below. And if anyone wants these links, post in the chat, let me know, and I can do that near the end of the talk. So once again, this is the example we're going to be going through. It's a Portuguese banking data set from UCI. The problem that we are being given is to classify users based off of if a bank term was opened or not opened, and then to identify the principal factors contributing to their classification. So with that being said, here, let me, the touch bar doesn't give me a escape button. I just gotta click through. All right, sorry about that. So with that, we can go into Python. And I'm gonna stop sharing my screen real quick just to go and check if there's any questions before we dive into the code. So, where's the Q&A? I think we have one question. Can we get a recording of this session? There will be a recording. Hi, Tesh. Thanks for asking. All right, cool. Once again, if anyone has any questions, drop them in the Q&A. Otherwise, we're just going to move forward in good faith, and I will assume everyone is ready to code. What about slides? Yeah, I'm pretty sure we'll be able to send out the slides as well. We can send that in the follow-up. All right, maybe I'll give it like 15 more seconds just to see if there's any questions. because I have a tendency to just kind of burn through this content. And resources linked to papers. Yes, that will all be available, whether it's in the follow-up email or on the IBM community or on the YouTube channel. All this information will be espoused to you. So I'm hoping everyone was able to download that data set because we are about to start. Yes. All right, cool. Well, with that being said, let's dive into code. So if you do not, for some reason, have, you don't have the libraries that we're going to use, you want this, matplotlib.pyplot, seaborn, and and pandas. So these are all what you're going to need. Everyone probably will have these if you have Jupyter on your computer already. I think it's a fair assumption that you guys probably will have all of these four. The two that we will need are these ones, just to do the modeling and the explanations. So I'm going to comment that out. All right, cool. So let's import pandas as PD. Whoops, import numpy as enq. So this should look familiar to everyone. We're just, getting pandas, numpy, matplotlib in, so that way we can do some simple visualizations and get our data in here and properly formatted. Oh, the last thing I forgot is sklearn. You can just throw it in here after a comma. We're going to need that because Lale is built on top of sklearn, so it'll work natively with all of the transformations, encoders, models, metrics from sklearn. And Lale also offers you the ability to make custom wrappers for each operator that you want to put in a pipeline or you want to automate hyperparameter selection for. Another cool thing is Lale and AIX360 both. Lale explicitly, AIX360 implicitly work with text data, tabular data, and images. And what I meant by implicitly is not all of the AIX360, because it is it's like a repertoire of multiple algorithms are going to work with all three of those ones. But overall, it captures those three. Lale will work with all of those. So if you want to do an NLP related task and you want to use a BPE encoder or BERT tokenizer or things of that nature, you can use that. Or you could use TF-IDF and funnel that into your actual modeling and do the different transformations, see which one works the best. And that's the idea behind rapid prototyping, which you will see in a second. But before we do that, let's get our data in here. So we do pd.read CSV. And if there's questions, once again, just type them in chat. And if it's something that's gonna, break the bank, Tim will let me know. So actually, what's easier to do is desktop, Python, or no. Yeah, I should probably just put it in the working folder instead of having to do this every time. But, gives me a little bit more time for you guys to catch up in case you need to.
Hey, Austin, we cannot see your screen. Are you sharing?
You can't see it?
No, we cannot.
Oh, snap.
Right now we see your camera.
My apologies. Can you see now?
Yes, we can see it right now.
I guess I got too excited. I thought everyone could see. Okay, so this is
so for about I guess maybe, I don't know how long, maybe 2 or 3 minutes.
2 or 3 minutes? All right. In that case, this is how you would install the underlying dependencies. If you already have something and you just type this in, don't worry. It's going to just going to tell you like, oh, it's already cached, and we'll pull it. but namely you're going to need these two in sklearn. So, you know, pip install this. When you put a exclamation point in front of it, this allows it to run and like on the CLI. And then this is just, you know, normal Python stuff, importing our data set. And then this is us getting our data frame in. So I'm going to run this, ta-da, do info, just to make sure that these are all non-null, which means, you know, we're not missing anything. And I'm going to let everyone capture this real quick, and I'm going to look at the Q&A. Oh, I guess it doesn't want me to look at the Q&A. Always does this. All right, well, I guess it's not going to want me to look at the Q&A while I'm sharing my screen, so I think it's important that I let everyone get this first. Maybe Tim can look at those Q&A and let me know if anything's like big, so that way I can stop and go and handle that before we move forward. Yeah, so we do df info to make sure that everything's not null, and then we can do df describe to describe our numerical values. So this just gives us, you know, a baseline information, a baseline understanding of our data. So the average age of one of our applicants is 40 years old with a standard deviation of 10. It gives us our different quartiles or quantiles. And yeah, so this is like, you know, a brief description of our data set, or at least the numerical ones. Not going to go too into detail. It's just good to know that this exists. And that it can be used for, you know, building some intuition about the underlying data. So for example, if our mean is 40 and our 50th percentile is 38, you know, we can make some assumptions about the shape of this data and things of that nature. So that's kind of just why we do df.info, make sure we have no non-nulls. And then df.describe to just get a little bit more information and, you know, kind of get the brain working of like, oh, okay, these are numerical values. This matches up with this. So these are either ints or floats. And it kind of just, you know, gives you like a little bit of a gut check of, okay, we're moving forward and everything should work. So the next thing we're going to do is we're going to cast X, Y, and we're going to just use some Python. Or not Python, pandas to do this. So what this is saying is go to the data frame, find the location for all the rows where the column does not equal Y. And then our X, or then our Y value is df dot, or dfy dot map dict. And then we can do yes equals 1, no equals 0. And then this should work. Okay, it does. And then if we just want to double check it, we can type in X and we see that we still have this. Whoops. So let's check our Y. All right, cool. Our Y is now Boolean. So, I mean, always was, but now it's a number. So cool, now we're good to move forward. So now we're going to import sklearn preprocessing. We're going to import the ordinal encoder, which is basically going to map our categorical values to some integer, and then that integer will represent it to our model, because we cannot use a mixture of categoricals and numeric for the models we are going to try. For most models in general. So, you know, getting it into a concise numerical format is helpful. Cool, so now that we have that imported, let's actually make our encoder. So ordinal encoder, xn equals x dot values. We have to fit it, so let's fit it to our xn. And then we can transform it. Yeah, let's make this one capital. And then we're going to make this a data frame just because it makes things a little bit easier on us. And I guess this is an important time to say it. Here, let me just finish that. So these data frames can have an underlying schema associated with them, and that is helpful for Lolly because it's just helpful in general because you know, one of the biggest challenges with using Python, which is a dynamically typed language, is types. So getting type errors. You know, we make the assumption something's a string, but it's an int, or vice versa, or all kinds of things can happen. So the cool thing is you can map a schema to. Here, I'm gonna scroll up real quick. I'll go back down. But you know, you can assign a schema where it'll tell you, you know, age is an integer, job is this, and that can be stored as a JSON file. And that's just helpful to have because you can pass that to your models, and it allows you, once you've built your modeling and everything, we'll see this at length once we get further, but you can pass this serialized JSON file that captures your schema along with your model, which can be captured as JSON, and together you can run that on a different physical or you know, virtual machine and produce the same results, which is cool for collaboration and making sure that, you know, we can adequately debug together. So, you know, what's the point of explaining something if there's some underlying variance to it? You know, if I run my model on my machine and you run your model on your machine and it ends up, you know, we have some different intermediate representation, then we're not actually describing or explaining the same phenomenon. Versus if you have a serialized JSON that captures your data schema and your model, that gives you a much better foundation to build your explanation on. And if anyone needs me to like repeat anything or anything of that nature, just let me know. And then we're just gonna make an all df, which is pd.concat. And then we're gonna concatenate xn and y. So this equals 1. And it should make sense why we're doing this in a second. Well, I guess we'll do this first. Import cborn as SNS, plt.figure, big size equals 15 by 15.
Hey, Austin, one quick note here. So someone mentioned it's a bit hard to follow along with your typing when it's going so quickly. And the question is this gonna be available on GitHub somewhere?
Yes, it will. Sorry, I will try and type slower.
Thank you.
But yes, this will all be available on GitHub. Thanks for telling me that, Tim. So yeah, we're just passing. So this is just an underlying DF implementation to get a correlation matrix. And then we're passing it to cborn. So it looks pretty. We do want the labels. We're going to choose colors. These are my favorite colors. It's just the color map from Matplotlib. And
actually, sorry. Sorry to interrupt you. Actually, sorry, I misread it. The question was, is it already available right now so that this person could catch up?
In theory, here, let me double check that I'm not giving them wrong information.
Thank you.
Whoops. So yes, it is this one called XAI Small, and it's at github.com/decentdilettante.
Could you put the, could you be so kind and put the link in the chat? That'd be awesome.
Sure.
Thank you. And thanks for the questions. Again, everyone, if you have questions like that, definitely speak up so we can address that better than not speak up.
There, sorry about that.
Thank you, everyone.
I have not used ML flow. What is that? I'm assuming, is it an explainability or maybe it's automated? Can you tell me more? which library again, please? Type answer. You're going to need Lale, AIX 360, Pandas, C, Born, the iPod, and S. All right, cool. Looks like all the questions are answered. We'll go back to sharing my screen. I'm not going to be able to see people's comments, but once I share my screen, I'll just have Tim confirm. Tim, you can see my screen, right?
I can.
All right, cool. All right, I'm gonna take a sip of coffee real quick while I let people catch up. All right, cool. So once again, just recapping. We create a 15 by 15 figure, get our correlation values, call it core, and then we pass those values into a heat map. We want the labels of their data. We're going to use reddish characters and then up to 3 digits. And this is what it should look like. As you can see, it's a little bit hard to read some of these. So what I like to do sometimes, depends on how specific you want to get, but if you just give it 1 digit past the decimal point, it removes the amount of information, but it makes it much easier to visually inspect. And what I mean by that is, with the color coordination, we can quickly see like, oh, contact has 60% correlation with consumer price index, things of that nature. And then I'm not going to go into a super detailed overview of what these underlying features are, just because it has that on the repository where you get the data from. So yeah, that it's just important that we do this. This is, I'm hesitant to call this feature engineering. This is just like trying to understand our features and see like, hey, is there underlying, underlying information that we can take advantage of. So, one thing you should look at is what is your dependent variable most heavily correlated with? So it seems like duration is going to have a large degree of information. And when you go on the website, it tells you to drop duration because for a classification model, one of the pieces of information you will not have at the time of a call when you're trying to make your classification is the duration of the call, because you'll have different information, you'll call them, but you won't know how long the call is going to be until the call ends. So for this to be realistic, you should remove duration by dropping it from your data frame. We're not going to do that right now because it's, we scoped that in. I'm going to show you one of the biggest strengths of the workflow in my eyes, and which is the idea is once you build this out, you can, going back to the iterative idea of explainability or recursive, we can keep rerunning this by, going up to kernel, restart, and run all cells. Of course, you don't want to do that every time because I'm sure, as you guys know, if your data is large or if you're using computationally intensive models, you may not have all the time in the world to run your model 20 times. But that being said, that's, in theory, that's a strength of this. And the other thing is you're probably not doing localized compute for your work. You're probably doing it on a cloud. So in that case, there's different ways around that. Once again, outside the scope of this. Sorry, sounds like my cat's going crazy. So sorry about that. So I'm going to move forward now. So once again, this will be on GitHub if anyone needs it. We're going to do our first model, which will be a rule-based model. And what a rule-based model is like, it's a set of rules. So it'd be, these ones aren't, there's underlying mathematical papers that you can read that talk about the implementation. The first one we're going to use is, it uses, it's a logistic rule regression. So it uses a logistic regression to create rules based off of the coefficients, and it assigns a coefficient to each rule. versus, you know, at a simpler level, a rule-based model could be an if, you know, if else, you know, if, you know, if it has 4 legs, 2 ears, and fur, it is a cat or a dog. If it doesn't, then maybe it's a worm. I mean, that's kind of a bad one. But yeah, that's the idea of being rule-based. Sorry, my cat is insane. Algorithms. We want rule-based methods. Import feature. Wait, no. Yes. All right, we want feature binarizer, and that is to binarize our features. And I will explain what that means when I finish typing this. Sorry, I know someone said I typed too fast. I have a tendency to hit tab for autocomplete. And then once again, these are at the AIX 360 library. So if you want to look at the underlying implementation or the source code, that's where I'd look. Excuse me. And so what the feature binarizer is going to do is it's basically for our categorical variables. It's so if we have for occupation, if we have doctor and lawyer, instead of, you know, having the ordinal encoders of 0, 1, and then maybe like let's have a third one, and the third one is garbage man. So 0, 1, and 2. Instead of doing that way for each observation, we're instead going to treat each one of those occupations as its own feature, and it'll express itself through a binary variable. So if they're a doctor, it will be a 1, and it'll be 0 for all the other occupations, which are now considered features. For numerical values like age, each age will be a yes or no. So if they're 72 years old, that will have a 1, and the rest of the ages will be 0. And what this does is it allows us to have more, I mean, we still have the same amount of underlying information in the data set, but it gives us more nuance to express these rules with by binarizing them. So that being said, let's get our XTrain and STest data. So, oh, I don't even think I split the data yet. Nope, I didn't. So, sorry. Let's do this. From So we need this. So now we have XTrain, X-test, Y-train, Y-test, where the test size is 20% of the data. Now we can keep going. So now we can, and then I'm adding FB to the end, just so we know it's the feature binarized version. I always do this. And we call fit transform, which does fitting and a transformation in the same step. All right, cool. So yeah, so that's just telling us the underlying implementation that they're all converted to float. All right, that makes sense. So now we can get into the actual modeling. Cool. So let's do LRR equals our logistic regression, rule regression, whoops. And then we have two hyperparameters. And what these hyperparameters govern is the complexity of the model versus the accuracy. So there's a trade-off. So we can create a very complex model that performs very well on accuracy, but the problem is it's so complex we can no longer, understand it or explain it, versus we could have a simpler model that may not be as accurate. And these two hyperparameters, lambda 0 and lambda 1, govern this. So this is something where you could, throw these in, you would throw this in a for loop and, chain and increment these by some number. Or you could use them, you could wrap this and use it in Lale, which we'll do in a little bit, not with this specific algorithm. But the idea being you can find hyperparameters to return, both a useful model in terms of accuracy, but also something that is explainable that can, give you underlying information of like this data set. All right, cool. So now that we have that, we can fit it with cool. So now let's train it or fit it. Cool. And now we can explain our rules by calling explain. And these are our rules. So and this is for the probability of y equals 1. So these are the rules used to determine if someone opened a if someone opened up a bank term, and if any of these rules are validated or invalidated, then it is that they did not open one. So so as you can see, it comes up with interesting rules. So if the month's not equal to March and the duration is less than 548 seconds, which is almost 10 minutes, then this is the coefficient. And as you can see, they're both negative and positive because this is based off of logistic regression. So let's get our accuracy scores and see what we get with this arbitrary model. Sorry. Oh. Cool. So our training accuracy is 90%. Let's see what our, let's see what our test accuracy is. So I'm just going to cheat and why type more when you can type less. And I'm just going to do this right here. Test accuracy, let's use y test. Let's use test. And we get 90, like a little less than 91%, which is pretty cool for a rule-based model. And you have this now. And from this, you could use this to build another model on top of. You could use this as your model. You could take these rules and hard code it and then run it again and see if you get the same results. And then that's what you deploy. It'd be pretty low bulk. There's all kinds of things you could do with this, but the idea being with a relatively you know, I mean, I really suggest you read the underlying paper because I mean, this is simple in theory, but there are underlying assumptions that this model makes that you should be aware of. But this is, you know, pretty helpful to us. This gives us a list of rules that can help us, you know, determine if they opened a bank deposit or if they didn't. And 90% test accuracy is a pretty good baseline. You know, we could change, because this is an unbalanced data set. So, you know, less than 10% of the observations are people who opened up a banking term. So, you know, with this, you know, kind of like a minimum viable product or like, you know, our exploratory data analysis, now we could go and use things like SMOTE or, you know, upscaling, downscaling to see, you know, if there's underlying things in our data that are making our results this good out of the box. Because the one thing I want you guys to walk away with is the most skeptical person of your work should always be you. By no means should we, you know, create an environment where we get 90% accuracy and we're immediately like, wow, this is the best thing ever, I'm done. We should always, you know, kind of scrutinize it and see if there's room for improvement. If we are doing something improperly, you know, maybe get another person's eyes on it to make sure that we are doing these things in good faith. But with that being said, now we are ready to go into, well, actually, no, I'll show you one last thing. So what we can also do is visualize these rules. So you can visualize each one of these rules. Well, yeah, not each one, but here. So this is the effect that duration has. So the contribution to log odds of y equals 1. As you can see, it actually detracts from the contribution to a classification up until around, you know, 200 seconds, and then it is linear, which is interesting. So this tells you, you know, going back to our correlation matrix, you know, duration had a 0.4, 40% correlation with our dependent variable, and this kind of, you know, seeing this graph and knowing that information, it makes sense. It's like, holy, you know, holy moly, like once you get above 200 seconds, which is basically like 3 minutes and 20 seconds, you could almost just use duration is kind of what this graph is telling us. I don't think that'd be a good thing because once again, we don't have the underlying assumption or we don't have that underlying information at the time of the classification. But it's food for thought. Let's visualize one more thing. So you pass in your X value, your binarizer, and then what you want to look at. So this is number of employed. And this looks like a stepwise function where the less employees they have, the higher likelihood that their bank term will be opened. So this is, you know, pretty interesting. And you can use, you know, you can use the visualize function to visualize all of those rules above to show you, you know, to visualize what's actually happening with the underlying rules. So that's, this is from AIX360, and the idea is, you know, this is a good place to start. I mean, this is a place you could end, and, you know, we could really debug this model and try and, you know, get simpler rules, things of that nature. But for the scope of this talk, I think I'm going to show you a little bit more tooling. And then if we have time, we can come back at the end and I'll show you, we can run this again. So now let us go into the next part. So we're just going to do some import statements for the that we're going to use. So from sklearn pre-processing, we're going to get normalizer and standard scalar. They, you know, the zero mean and unit variance, one is row wise and then one is column wise. So they accomplish the same task, but they do it differently. Then we're going to get no operator. That's from we're going to get pretty print. And then we're going to get 3 different models. And then the most important part of importing these is we need to make sure we wrap them so that we can use them with Lale. Oh my goodness, I cannot type right now. Oh, I didn't import layout. Cool. So I'll give everyone a second to just make sure that they got that down. And then if you have any questions, type them. And then if they are showstoppers, Tim will let me know, because once again, I cannot seem to click on it.
Yeah, not sure if they're showstoppers, but there are 3 questions.
3 questions. All right, well, maybe I'll give everyone like a minute or 2 more, and then I can stop and answer those questions before we go into this.
Thank you.
Of course. So. All right, well, I'm going to stop sharing, and then I'll come back and pause on this again so everyone can look at it. But I'm just going to go and try and answer those questions really quick. So, sorry, question. How can we install now? What if I don't want to install my, like, what do you suggest, please? Yes, I agree with Candace. I haven't used it in Google Colab, to be quite frank. That's something I can go and get information on if it's not already on the Lale GitHub. I would check the GitHub and see if they have that information there. If not, I can get that information for you. I also think that Candace offered some great input. Send. About heat map. When it gets so large, it's hard to follow it and learn from it. What's the advantage of it then? Thanks. So the idea behind it is it's not a panacea. It's not going to like solve everything, but what it does is it allows you to get like a really good baseline. So it's not explaining everything, but what it does is it gives you a good picture to interpret. You know, you can look at those correlations and say, oh, well, there's collinearity between these 2 variables. So maybe if my model is going to be deployed on the edge and it needs to be low compute, I'm going to remove some features that are correlated with each other. That's what it does, you know. Or if there's too much predictability in certain features where I think we're at risk of overfitting, I'm going to remove those. Things of that nature. That's what it helps with. It's not, once again, it's not a panacea. So I'll type in, sorry. It is not a panacea. It just gives a great point of reference for more fine-tuned information. If the results of LRR explained duration has been repeated several times, what does it mean? Is it like the decision? Yes, that's exactly what it means. Yes, that is exactly what it means. The paper goes into more detail about that.
Thanks, Austin.
All right. Awesome. We will go back to Jupyter Lab then. All right, cool. So now we make a pipeline, which is we're gonna do normalizer, standard scalar, no operation. Where these vertical bars denote a choice for Lale. This is basically like feed forward. And there's more, I'm sorry, did you say something, Tim? I guess not.
No, you're all good. Thank you. Thanks for answering that set of questions there. Thank you.
No problem. Thanks for asking them, everyone. And then, so these are our, transformations. These are our algorithms that we're going to make a choice between, and then we can show them. So this is very similar to sklearn's pipeline if you've used that before. Visualize. All right, cool. So, and these colors infer information. So actually this light blue infers that these are in a trainable state, except no op, because you can't train it. It doesn't do anything. So that's what those colors mean. And then what we're going to do is this Lale works with the underlying implementations for like grid search, CV, SMAC, and HyperOpt. We're going to use HyperOpt because HyperOpt, you don't have to explicitly define your solution space, and you don't have to give it like a value to iterate by. It will handle all that behind the scenes for you. And so once again, it helps you determine the why. It frees up time for the why. So we're going to use HyperOpt and Lale to, you know, semi-automate hyperparameter selection, and based off of these hyperparameter selections, pick, you know, the best algorithm out of the suite of 3 we gave it. And from there, we can fine tune these algorithms to, you know, do better, perform better based off the metrics we want. We could, you know, find similar algorithms. We can do custom. That's the idea. It's not how we accomplish, but why. And that's what this frees up time for you to do. It's not so much important using Lale at least of the way I solve this problem is by creating a pipeline with normalizer, standard scaler, no op, and 3 algorithms. It's, you know, I did that so that way I can understand why decision tree seems to work the best for this, and where the edge cases are for the tree, and, you know, pruning that tree so that way when I visualize it, a human can understand what where the splits are, and, you know, or, you know, if you want to go into more technical, I'm trying to understand, you know, the entropy of the tree or the Gini index, etc. But once again, we're going to use HyperOpt. Optimizer equals HyperOpt. The estimator is the pipeline we want to train. Max evals equals 5. This does do k-fold cross validation. I think the default value is 3. So just so everyone knows. And so we do that, voila. And then we do trained pipe equals optimizer dot fit. And then we hit enter. Uh-oh. None of the trials succeeded. That's not good. I'm sorry. 1 sec. Yeah, sorry if I'm making anyone sick by scrolling so fast. I'm just trying to fix this. I'm not sure why that just happened. That definitely should not be the case. So I'm going to try and restart and run it all. So let me know if it works for you guys, because no, whoops, maybe I should have ran that one. All right, well, I guess we're going to debug together, because that definitely should not happen. This is not good. So verbose is going to tell me why it failed and where it fails. So expected the sub to be a subschema of super. Okay, so this underlying schema is why it 1, 2, 3, 4, 5, 10, 20. Interesting. That's, I don't know if there's a new version. So here, let's yeah, if I can't get working on this runtime, I have another notebook that like has all this stuff in it. This is not good if I'm demoing it live and it doesn't work. Here, I'm gonna stop sharing real quick and see if anyone else said it didn't run. End-to-end machine learning. I'll make sure to check it out. With pipe, are you making a pipeline for a bunch of algorithms? Yeah, so what it's going to do is it runs that pipeline. It runs it each time with each different transformation, each different algorithm, and tunes hyperparameters, and then based off of that, it returns the one with the best training score. So it is very similar to scikit-learn machine learning workflow. It just, I'm not showing it, but you can make very complicated pipelines with it, and you can custom wrap it. So that way, if you wanted to use like a custom implementation of one of these underlying algorithms, you could cast it as its own variable. And then why do we need no op? Sometimes these, not doing any transformation will actually make the algorithm work better. So using no op is helpful. So I hope that helped. It is similar, and we need no op because it sometimes it produces. All right. So in that case, I'll just show you guys I'll show you guys like I mean, this is really, it's bothering me. I'm gonna try it one more time. Oh, I know what it is. I found the bug. So the reason it didn't work is because the schema I was training it with was not right. So what does that actually mean? Right here, when I did the train and test, I passed it X instead of X encoded. And since it's not encoded, it's not going to work in those pipelines because of the schema. Like I said earlier, numbers and categorical values cannot be cast together. But I mean, that's pretty cool for us, right? I mean, you saw me debug it live, but the reason I knew is because when I passed in verbose and it told me that the schemas didn't agree, it was the underlying data. The problem with that is I made the assumption I did it correctly the first time, which is an unfair assumption. So thank you all for bearing with me as we got through that one. So now we can add these back. And in theory, okay, now it's running. Okay, thank goodness. Thank you everyone very much for your patience. So that was user error. That was not the underlying algorithm. So it happens when you do a live code demo, I guess. Train pipe dot summary. And this is going to tell us the best and the worst. So we can look at it. and determine which one did the best. So you could, and all of these things are queryable if you want. Like you could, you know, like best equals trained. That's summary. Oh, what did I do wrong? B3. So yeah, this kind of stuff you can do. You can also do train pipe dot get pipeline dot visualize. So what did we do? We used standard scalar into a logistic regression. So we visualized it. Let's get some predictions. Predictions equals trained pipe dot predict x test print. And then once again, I'm a big believer in not typing more than you need to. So we're just command copy that. And then we can do ROUC and then ROC-AUC, hit enter, boom. So as you can see with just using HyperOpt, we got 90.9% accuracy on our test data and around 70% ROC, area under the curve. So which tells us we're about 20% better than a random guess. And then we cross-validate on the training, but if we want to cross-validate on the, well, I'll wait to do that. Actually, let me show you this. Train pipe, get pipeline. And then we can pretty print it. Show imports equals false, IPython display equals true. And this tells us our JSON. Now you can export this as a trace JSON file. This is just like shows it in a prettier fashion, but gives you standard scalar with the hyperparameter with mean equal false, and then it gives you the logistic regression with your C value, what solver you used, and your tolerance. And you know, this is what we could fine tune in theory. We could get logistic regression out. We could do more transformations. We could change the logistic regression, but you know, we're just gonna keep it with this. We're not gonna fine tune it right now. But what's interesting is that rule-based algorithm actually got very close to accuracy. We could remove logistic regression. You know, say we want to know what does better between a tree and the k-nearest neighbors, and this will actually take less time because there's one less algorithm. So we can have that run in the background and just see what happens. I'm going to add it back for one last thing that I want to show you guys. So now we have that. Do this. Now k-nearest neighbors. It got 2% less accuracy, but a better ROC. So based off of what scoring you use, you know, maybe if we had scored it by ROC, we would have returned the k-nearest neighbors. But and then we can see what the underlying hyperparameters are. And then we can, I'm not going to do cross-validation just because I realize what our time is and I want to save time for questions. So what we'll do instead is AIX360 algorithms. Yeah, all I was going to do with cross-validation anyways is show you guys that that accuracy is correct. So Lime tabular explainer from AIX 360 to algorithms. .shap import kernel import shap. So we need to set up our class names, which we're going to use as a parameter that we're going to pass in. So we put in 0 and 1. We pass it some arbitrary index for what we want to see at a local level. So what Lime is basically it takes your underlying data and it perturbs it, and it sees how much, and by perturb I mean it changes it by a small amount, and it sees, you know, incrementally what amount to each feature needs to be changed for the classification to change as well, and that allows us to infer feature importance. Idea meaning the more sensitive it is, Lime is to a feature changing, the higher that feature's contribution to the actual underlying classification. There's a paper on it. Once again, I listed that in the slides, and I can share it with anyone who needs it. But sorry, I'm just trying to get this for you guys so we have time to go over questions. So. And then yeah, you can pass whatever, as long as your number of features isn't more than your actual features you have, then you'll be fine. Here, let's make this prettier. Whoops. So the predicted class is this one, which is 0, and the true value is 0. And if we want to see what that looks like, so we have with almost 100% certainty, it thinks that this one is 0. So that means they didn't open a term. They didn't open a term because that's the true value. And this is the feature contributions. And it tells you the actual value for each feature for this one, and tells you the log odds contribution. Just a quick bit of like math. For binary classification, the log odds of one class is the inverse of the log odds for another. So that's why it's 9% contribution to 1 for a value of your Bohr 3M for 305. And it's the opposite for the same thing for classification 0. And that's listed in the Lime paper. And the last thing we're going to do is we'll use SHAP to accomplish a similar thing, but SHAP is based off of game theory, and it also does feature importance. And once we get done with this, we're basically going to have accomplished our task of, classifying our observations on whether or not they opened or did not open a term, and then determining what the the largest contributing factors were. And then, whoops. It's taking longer to run than normal. Okay, it's done. All right, and this is our feature contribution. So this is for the first index. This is not for our the one we used earlier, but it tells you. So these are local explanations, so these aren't global. This does not imply the feature importance for all of them. You can do that with the for loop once again, or you can create your own class and subroutines to do that at a global level with these. But these are both like Lime's name is actually locally interpretable model agnostic explanation. So it's a localized level. SHAP can be used as a global level. That is in the paper, and it is in AIX, and there are other routines in AIX to get global solutions. The problem being with the 40,000 observation data set, which is relatively small, some of those can be computationally intensive, especially when running locally, which I did so that way people could follow along on their own machines. But with that being said, the last thing I want to leave you with before we go into Q&A is, while I let that run, you know how I said we could like just run this? So we could just do equals x and drop. What other ones do we want to do? Let's do housing. You know, in theory, you would never want to do this in the workplace where you're just dropping them willy-nilly, but I'm doing it because I want to kind of prove a point. Let me scroll down. Get that finished. And so, you know, look, we got very similar results. Euribor 3, M, duration, and then how much it actually contributes for the same one. So those agree, and that's just like a quick litmus test. But now that I've dropped these, sorry, I don't mean to scroll so fast. I don't want to make anyone nauseous, but I just decided to drop 6. We can save it, kernel, restart kernel, and run all of them. And this is the last thing I'll do. But this is just kind of show like you really can just drop them. Once again, I don't think you should do that, but it's just to communicate a point. So we got much less rules. We lost, you know, I think % of accuracy. We no longer have duration because we dropped it. That's fine. It doesn't throw an error and cancel this. Number of employed is still, you know, still has negative contribution. Actually, it's become not positive at all. It's only detracting. We can look at this. We still get a standard scalar with a logistic regression. We give up, we lose out on our ROC score, but our accuracy score doesn't seem to be too solved. If you look at the actual hyperparameters, they look, I mean, you know, we didn't write them down or save them, but almost very similar to what we saw before. But look, now this one, which was correctly labeled before, is incorrectly labeled. With 94% certainty, our algorithm thinks that this is class 0, but it's actually class 1. And so, you know, we can use this and, you know, interpret why is that the case, and then we will you could dynamically use this tool, this toolkit to arrive at an explanation. And there's, you know, there's algorithms that we didn't touch on just out of the sake of time. But with that being said, this will be on GitHub. Everyone will be able to get it. And I really appreciate everyone's time, and we will go into Q&A. I'm going to stop sharing my screen. We can. When you say pipeline train .get pipeline, it gets the best scoring one for you automatically. We can use Lime or Shopping Explainer. Why do we need AIX360 then? AIX360 wraps those two, and it also has other underlying implementations of different algorithms. So there's I didn't show it in this one because this was interactive and it takes a while, but they have CEME. And then the other thing is there's the faithfulness and the monotonicity metrics, which you can use to evaluate your Lime or SHAP algorithms. So faithfulness is the idea of are the computation, what is the similarity between the computations that occur in your pipeline and that occur in Lime to arrive at that classification? And then that's faithfulness. And then monotonicity is, are your features additively monotonic? Meaning if you have 5 features, does each feature contribute a positive increase in accuracy? And what you can do is, based off the explanations from Lime or SHAP, you can utilize faithfulness and monotonicity for feature engineering and also to understand the resiliency of your explanations. And those two metrics do not come in the box with Lime or SHAP. So that is why we would use them in AIX360. Plus AIX360 gives you access to other algorithms that are not just Lime and SHAP. So I hope that helps.